Imagine you've spent 100 years building the most complex puzzle ever assembled. The brightest minds on the planet, the most powerful telescopes ever pointed at the sky. And finally, the picture is complete. The universe understood, its age known, its size measured, its speed calculated. Then one man picks up a ruler, looks at the numbers, and says quietly, almost casually, "The math doesn't add up." Not slightly off, not a rounding error. Off in a way that means the entire picture might be wrong. That man is Adam Riess, Nobel Prize winner in physics. And he's not being dramatic, he's just reading the data. The universe is expanding faster than it should. And right now, nobody knows why. There is one number. Imagine just one single number that everything else depends on. The age of the universe, its size, when the first stars ignited, when the first planets formed, when life became possible. It is called the Hubble constant, and it measures the speed at which the universe is flying apart right now. Not in the past, not in theory, right at this very second, as you watch this. You might think measuring the expansion speed of the universe sounds like something impossible. But physicists have two ways to do it, two independent methods, two teams, one universe. There should be one answer. The first method looks into the past, the distant past. The Planck satellite mapped the faint glow left over from a time when the universe was just 380,000 years old, almost an infant by cosmic standards. Physicists took that map, fed the data into the equations of the Standard Model, fast-forwarded 14 billion years, and got an answer. 67 kilometers per second for every 3.26 million light years. Precise, clean, confident. The second method looks at the present, directly. Adam Riess and his team measure distances to real galaxies using pulsating stars, Cepheids. These stars pulse with the precision of a metronome. From the pulse rate, you can calculate their true brightness. From the brightness, the distance. From the distance and recession speed of the galaxy, the Hubble constant. Their answer, 73. Not 67, but 73. The difference seems small. But in cosmology, where measurement precision reaches 1%, this is a chasm. It is as if two independent chronometers, tested and calibrated, were showing different times, and both would be right by their own data. This is not one team's mistake. This is not instrument error. This is something deeper, something that lives inside physics itself. And this discrepancy has been given a name: the Hubble Tension. Nobel laureate David Gross said it plainly. Do not call this a contradiction. This is a crisis. As the crisis became clear, the scientific community had a theory. There was an explanation, a comfortable one, almost reassuring. Cepheid stars, the pulsing stars that hold the entire measurement ladder together, live inside young galaxies. Young galaxies are dense, dusty, packed with stars. When the Hubble Space Telescope observed them, it sometimes mixed the light from nearby stars together. A Cepheid appeared brighter than it really was. Brighter means closer. Closer means the Hubble constant looks higher than it should. Fix the blending, and 73 becomes 67. Crisis closed. Everyone goes home. It was a beautiful theory, and there was a perfect instrument to test it. The James Webb Space Telescope. floating 1.5 million kilometers from Earth, a golden mirror 6.5 meters wide, seeing through dust, through density, through everything that could have fooled Hubble for decades. Many scientists were already writing the obituary for this crisis before the data even arrived. Webb pointed its mirror at the same Cepheids, the same galaxies, the same stars, with a precision humanity had never had before. And what did it see? The same thing. The Cepheids looked identical. The distances didn't change. The expansion rate stayed at 73. The telescope that was supposed to close the crisis confirmed it instead. Adam Riess said it simply: once you rule out measurement error, only one explanation remains. We are misunderstanding the universe. Think about what it means. The universe is expanding faster than it should. The Hubble constant isn't just a number in a scientific paper. It's a key. Pull on it, and everything else starts to move. If the universe is expanding faster, it's younger, not by a few years, by 1 billion years or more. Stars ignited earlier. The first heavy elements, carbon, oxygen, iron, formed faster. Conditions for planets arrived sooner, and the window for life to emerge, wider than we thought, or narrower, depending on which explanation turns out to be right. The nature of dark energy changes too. That invisible force making up 68% of everything that exists. We know it's there because the universe is accelerating apart. If that acceleration isn't what we thought, dark energy isn't what we thought either. One hypothesis is early dark energy, a burst of additional expansion in the first few 100,000 years after the Big Bang. Cosmologist Mark Kamionkowski compared it to a push the universe received right after birth. That push echoed through 14 billion years, and we're hearing it today. But the Standard Model isn't dead. It explains the cosmic microwave background with extraordinary precision. It predicted the ratio of hydrogen to helium in the universe. It works. Just not completely. The 1990s had something similar. Measurements suggested the universe was younger than its oldest stars. Absurd. Then dark energy was discovered, and everything fell into place. What looked like a fatal crack turned out to be the shadow of something enormous. Somewhere between the first second after the Big Bang and today, something is happening. Something we never saw, never modeled, never imagined. The universe isn't broken. Our map is just incomplete. And the next version of that map will be stranger and more beautiful than anything we've drawn before. We'll be here when it arrives. If you want to follow along as humanity rewrites the map of reality, subscribe to Star Voyager. See you on the next journey.